Okay, so welcome back to class. As I mentioned, we went through a couple announcements before I started the recording. Today's plan is to review attendance. I think we got everybody on that's on the roster last time, so we shouldn't need to do that. I won't take attendance at the beginning of every class. It's just to make sure that, again, if there are any registration issues, we get those sorted out earlier rather than later. We'll continue on with our discussion of the definition of and some applications of statistics, and then we'll start our Chapter 1 PowerPoint. And then each day I like to do a quote of the day, just a little idea that I kind of find useful. And maybe, some of these resonate with you, maybe some of them not so much. But hopefully everybody gets at least a little something out of this. I do consider math to be kind of a general education, like service discipline, um, at the 100 level at the very least. And so I think this is a component of that. One of our previous deans kind of recommended a bit of a shift in thought, and I found that um, to be a very valid idea. So the quote of the day today is from P.T. Barnum, the famous circus promoter, and he says, "True economy consists in always making the income exceed the outgo, where the all close a little longer, blah blah blah, so that unless some foreseen accident occurs, there will be margin in favor of the income." Now, I don't think this idea just applies to finances. I mean, especially as students, finances are a bit tricky at this point, right? And sometimes this isn't really feasible. But I think the concept of building margin in life where you're able to is a very important concept. So for me personally, I find that I'm much more frustrated with people on the road or with lights, or maybe make not the greatest decisions when driving if I'm running late. But if I leave even 3 minutes early, like what is 3 minutes to me during the day? It's nothing. But if I leave 3 minutes early, uh, then all of a sudden it's like, oh, well, I hit a light, no big deal. Or somebody in front of me is driving slow, no big deal, right? It just changes perspective quite a bit. Uh, so there's this kind of idea that when you have margin, catastrophes often become inconveniences, and when you have no margin, inconveniences often become catastrophes. So one, really important example of this is due dates in classes, right? If you have a term paper, if you have an exam that has a certain due date, if you have homework that has a due date, if you wait until the night before that term paper is due or the night that the exam is due to plan to start it, well, if you have a tech glitch, if you have something personal happen, if you have, anything goes wrong, you have no margin. There's no margin there. And that minor inconvenience, that thing that would otherwise be a minor inconvenience, at least in this, from that perspective, the perspective of the academics, becomes a major catastrophe, right? You miss a term paper, maybe fail a course because of that, or miss an important exam, get a zero, and it drops your grade by 2 letter grades. That's something that you don't want to have happen. On the other hand, you say you plan to take the exam on Thursday and it's due Sunday, and you have a power outage. Well, you just take it on Friday, right? It's kind of an inconvenience. You need to move some things around, but no big deal. So I think this is, one of the keys to success in life and in college is being diligent about time management and building in margin. So that's kind of the thought for the day, the quote for the day. Let me see. I see that there's a chat. Okay, somebody asked that I take attendance. I don't take attendance each day. I just take, we took attendance the first day, so we're good on that. So that's just kind of left over from the kind of standard plan for this class meeting. Okay, so let's jump into our discussion of statistics. So we talked last time a little bit about a definition of statistics, and I kind of gave what I think is a good definition. There are different, definitions. This isn't the book, the definition the book gives, but um, I would say the statistics is the process. Oh man, my handwriting is abysmal at the moment. Is the process of converting nearly useless raw data into a more usable form. Um, yeah, sometimes if I have my little writing pad just a couple of degrees off, it's throws a wrench in everything. But yeah, so we discussed this a little bit last time. Um, and I think this is really the goal of statistics. Now, there might be some things that we cover throughout the course where you say that doesn't immediately, reach this end result, but it ultimately has the goal of reaching this end result. So maybe we develop some mathematical structure and we say, we're not dealing with data in this instance. That's, yeah, but that structure is going to be later used to help us analyze data. And the idea is something like this. I'll use a different example. Let's say that we have S&P 500 data for, say, the last 10 years. So we just have a list of closing prices, prices at the end of day for the S&P 500. This is something like an aggregate price for the 500 biggest stocks, roughly speaking, in the US. Um, and maybe this is 10 years of data, and there's about 250 trading days a year. So this is something like 2,500 data points. This is what we would call our raw data. And some, as an aside, some people say data, some people say data. I probably say it, 50-50 one way versus the other. So, but it means the same thing. So if you just give me a list of 2,500 numbers listed on several pages of paper, that's really not helpful to me at all, right? My brain can't do anything with just a list of 2,500 numbers, but that is raw data. That's the kind of the direct measurement of the thing we're interested in, the price of the S&P 500. So it's the most direct measurement. It has the least interpretation. In a manner of speaking, the broadest group of people would agree on this data, but it also has very little utility. It's not very useful to me. But I might take this and convert it into something like maybe an average return. So on maybe something like average daily return, let's say. So kind of on average, from one day to the next, how much did the market go up or down? Did it on average go up 0.1 percentage points or go down 0.2 percentage points or stay flat? What does the average return look like? Maybe that's something that I could talk about. And specifically something like average return for the past 10 years. And this is what we would call a descriptive statistic. So this is just looking at the data itself as it is on the page, and applying some formula. So the average return is what it is. Again, uh, just about everybody would agree on this number. Nobody's going to say, oh, I think you have that number wrong. I mean, provided you did the calculation properly, the average return is the average return for, say, the past 10 years or for this data set. Now, the nice thing about this is a lot easier for me to understand. If I say the average return is, 0.1 percentage point per day, it's certainly not that high, but, let's just, or maybe we can say, 5% per year or something like that. That's a much easier concept for me to understand. If I, kind of in a typical year had invested $100 at the beginning of the year, I'd have $105 worth of shares at the end of the year. Now, from there, I might want to make an inference. It's all well and good to say something about this data set that can, be helpful to me, that can help me understand things. Uh, but it's going to be more helpful in this instance, maybe for me to say, well, based on what happened in the past 10 years, can I make kind of a guess as what will happen in the next year, right? So we could say, what do I think? Or maybe make a guess. I'm going to put kind of guess in quotes, right? This could be anywhere from just making a guess and not having a really good methodology for it to really what we're studying in this course is how do we construct a solid methodology for making such guesses. So maybe we guess what the average return for the next year will be. In other words, I take the data that I've collected and some of the analysis, the descriptive statistics that I've performed on it, and I make an inference. Inferring something about something like the nature of the underlying mechanics from this raw data and these descriptive statistics. I don't have a direct measurement that tells me exactly what will happen next year. I have direct measurements that tell me what happened in the last 10 years and some calculations I performed on those. And I'm using that to make an educated guess for what I think will happen in the next year. And then kind of related to that, I'll write it kind of like this, is something like, let's just say maybe investment strategy, right? Like, should I put all of my retirement money into equities? Should I have a diversified portfolio between, say, equities and or like stocks and bonds and maybe some foreign assets, maybe some real estate? What should the investment strategy be? And this is kind of what, and there's no rhyme or reason to these color schemes down here, so I don't think the green means good and red means bad. I'm just going through my markers at the top here. Investment strategy is kind of in the what I call like the wisdom category, and statistics can't really help us make these kind of decisions, right? Statistics can help us go from raw data to descriptive statistics to inferential statistics. We can understand more about the data we've collected, and we can maybe use those understandings to formulate models of reality that we can use to make predictions or make guesses. But what should we do with that? Often that requires making trade-offs, considering a lot of considerations that are external to the data. So, over here on the wisdom side, what should the investment strategy be? Well, what's your tolerance to risk? Or are you one of the people who, if the market bounces up and down, you're going to be losing sleep at night? Maybe a safer, less volatile investment strategy is better for you for that reason, even if, numbers wise, it wouldn't be completely optimal. Are you close to retirement or far away from retirement, right? So things like this we might want to look at. But that's kind of on the wisdom side. That's taking a more holistic view. And we would want the inferential statistics to help inform these decisions and the descriptive statistics and the data. But they're not the final arbiter of these decisions. And kind of in that vein, we have the data, information, knowledge, and wisdom kind of way of thinking about things. And our goal in statistics is to process data and turn it into information, descriptive statistics, so we can understand a little better, take that information and turn it into knowledge, maybe models that we can use to make predictions. So how can we have information and data about the last 10 years. How can we make a guess of what's going to happen in the next year? Or maybe if we're in a medical study, maybe we have, say, 3 experimental groups. We give 10 milligrams of the drug to one group, 20 to the next group, and 30 to the next group. And you know, the 10 isn't too effective. The 20 is pretty effective without too many side effects. And the 30 is effective, but has a ton of side effects. Well, what do we think would happen at 15? Do we think it would be as effective as 20 with fewer side effects? So maybe we look, in a sense, inside of our data and we try to make an inference that way, right? We don't want to run a whole new study if we think that 15 is going to be no better than 20 as far as side effects. And less efficacious. Um, so there are, several ways that we can look at what knowledge or what inferences we would like to make. But anytime that we're leaving the data set, the information gleaned directly from the data, we're making an inference and we're trying to say something, we're trying to make a claim that's bigger than what we can substantiate just based on the data alone. Um, and another example of this would be something like, I think the example we used last time was maybe we measure heights of people in Pittsburgh. Maybe we take 1,000 people, we measure their heights, and that gives us a data set. We can maybe compute an average height from that data set and say these 1,000 people or whatever, their average height is such a number. And then we maybe can infer from that that we think that the average height of all people in Pittsburgh, we didn't measure all people in Pittsburgh, but based on this sample of 1,000, we think that all people in Pittsburgh have such an average height. And then from there, we might want to use that to make a decision about how to, you know, how to build a public space or something like that to accommodate certain sizes of people, right? And there we're facing trade-offs. We can accommodate uh, a wider range of people, but we might need to have fewer, say, seats in a bus or something like that. So then the price per person goes up. So there are trade-offs to be had, and that's where we kind of leave the realm of statistics. We can't answer that question just with data and statistics. We need to know more about the situation. Okay, so that's where we left off last time. And I want to start a discussion on applications of statistics. So I kind of asked you to take a look at some applications of stats in your preferred field or your major, or your area of interest, and um, and to kind of come back with an application or an idea that you think is interesting. So let me pull up the chat here just in case anybody wants to pop in to the chat. Um, so does anybody want to volunteer their field, an application they came up with, or if you didn't have time to look into it, somewhere that you've seen statistics used?
For
Yeah, we
me,
can definitely use statistics and research. Somebody posted in the chat. Sorry, what was that?
I was gonna say an example as I did a lot when I did biology. I had to look up like many statistics and research on different kind of diseases and those kind of things to show.
Yeah, definitely. So for bio, epidemiology. So looking at things like incidence and prevalence of certain diseases, how many people, get a certain disease in a, say, a given year, or how many people have a certain disease at a given time. They definitely use tons of statistics. We saw with COVID, right? Um, there were constant reports about, is the number going up or is the number going down, or is the R not, bigger or less than this number, or um, okay, the vaccine comes out and it has a certain percentage effectiveness. In other words, of the people who would have gotten COVID if they didn't get the vaccine, what percentage of them don't get COVID now that they do have the vaccine? Um, roughly speaking, I'm not getting into the vaccine debate here, but then there are other benefits of vaccine, right? Maybe you get it and it's the disease process isn't as severe or something like that. But just to give some examples, I think COVID really kind of brought to the forefront a lot of this use of statistics and numbers and ratios and so on in the medical world and in epidemiology. So yeah, great example. Have somebody in the chat. Okay, research for psychology. Yeah, definitely psychology, psychiatry. Um, Definitely in that field, there's a lot of statistics that are used. I think our psych department even offers like a stats for psychologists or something like that. They kind of have their own stats course, I'm pretty sure, because some of the things that they do are, a little bit different than what we cover in this course. But yeah, they use a ton of stats there. As kind of a side note, when you have when you have very simple systems, you usually just kind of do an experiment and that's that, right? If you're taking a physics course and you want to know how gravity works, you set up a ramp, you measure the angle of the ramp, you roll a ball down it, and do that a couple times, and basically there's your answer. Um, when you have a very complex system, like say, maybe the human body, like maybe a population of, whatever 300 and something million living organisms or 7 or 8 billion living organisms, like all interacting, or when you have something complex like the brain, um, there are so many factors that come into play that we can't kind of that we can't control for is what we would call it, I suppose, in the experiment, that we end up using a lot of statistics to kind of try to pull out that noise and look at just the individual aspect that we're interested in. So, uh, yeah, somebody else posted over here, sports betting, definitely. Uh, yeah, so sports betting, it's kind of interesting that, a lot of people think that when they set, say, the line, for instance, for sports betting, like uh, what's the um, why can't I think of the word? But what's the number of points that this team needs to win by?
Money line
Or the
over
spread.
under.
Yeah, yeah, yeah. So the spread, like, what's the spread for the game? Um, a lot of people think to themselves, oh, well, they probably set the spread. Maybe they look at the teams, or maybe they look at the performances of the teams, or run a bunch of stats and say, we think that on average, team A will beat team B by, 6.5 points or something. So we set the spread at 6.5. But really, the casinos just want to be neutral stakeholders. So they want to set the spread at a level where they think the people betting on this side, or the amount of money betting on this side and the amount of money betting on that side, will be equal. So that at the end, regardless of whether the spread is covered or not, the losers pay the winners and the casino just takes their cut. Um, so yeah, predicting how people are going to bet is going to be possibly an even more difficult task than um, predicting who's going to win the game or who's going to win by how much. Yeah, in blackjack, there's a famous book. What is it called? Bringing Down the House, about the MIT blackjack team. I think it was made into a movie too. Um, and they would use statistics and card counting to basically to make money on blackjack. So that's kind of a cool application of statistics. Yeah, definitely. Somebody in the chat says basically market research of many forms. One example is what's the demand for different restaurant menu items? And you could look at this a couple of different ways. Kind of in the shorter term, well, how many lobsters or how many slices of steak should we buy for the next 2 or 3 days? If we buy too much, it goes bad and we lose money on that inventory. If we buy too little, then we run out of that. And if we're always running out of stuff every time somebody comes, to our restaurant, three of our menu items are out and they're like, oh, that was the thing I was going to order and I came here for. Um, that's probably not too great either, right? So can we can we figure out what's the demand going to be, say, on a short-term basis or on a long-term basis, if folks just aren't interested in this type of food or this menu item anymore, or if they're interested in a different type of item or a different type of food or a different type of service. Um, if we serve the market better, we are likely to capture more market share. So, um, one of my economics professor in undergrad, he he basically had three jobs at doing three things at the same time. He was an economics professor at Robert Morris. He owned his own restaurant, and he would write a column for one of the local papers, and just like a weekly column about economics or whatever he felt like writing about. And so when he at the end of his column, he would say his name, and he would say restaurateur and professor. And somebody wrote to him one time and asked him, like, why don't you write professor first? Like, that's the more impressive title, why is it professor and restaurateur? And he said, I think being a restaurateur is the more impressive title because if I make one bad decision for my restaurant, I could, restaurant industry is such a competitive industry. There's so many different restaurants. I could go under based on one bad decision, and that also will cost the jobs of a couple dozen people. So he actually viewed, being a restaurateur and keeping this restaurant open for 40 years or something, and profitable and employing all these people and giving them steady jobs as, his bigger contribution to society and the thing that he was more proud of. Yeah, definitely on the kind of marketing side, advertisement. So advertising. Um, right? I mean, obviously, if you're spending time and effort and money on advertising, you want to reach the proper market. Um, you're probably not going to advertise sports cars to a bunch of kids on, whatever kids channel, that you could advertise on. You're not going to advertise toys to 20-year-olds, little like kids' toys. Maybe you advertise kids' toys to, 40 or 50-year-olds or something when we want to relive our childhood and nostalgia and all that. But that's a whole different ball game. But yeah, so how do you target your advertising? And especially with things like social media and, whatever the detriments are of it, we have these companies that collect data and can target advertising effectively. Um, so how do we want to target that advertising? How do we evaluate whether this advertising strategy is beneficial or not, right? Are we making more money from this advertising than we're spending on it? Is it valuable? Um, so all of that would be something we might want to look at. Any other thoughts? Right. So some things that were I think kind of mentioned in our introductions last time, um, things like social policy, right? Should we spend, and the word I was trying to look for last time was wraparound services. Like, should we spend money on things like wraparound services for the school district, right? Um, if we spend X dollars on this service, will it increase outcomes or positive results or something like that more than if we spent that same money somewhere else, right? We can't just spend infinite money. Um, so we have to decide where to spend the money, and maybe we can use statistics to at least inform that decision. And again, this is another great example of statistics isn't the deciding factor, right? It's not that whatever will say increase test scores the most is where we put the money. You know, there are many other factors that come into play. What are our societal norms and values? What is the impact on students' lives and so on? That all comes into play, but maybe statistics can help inform that decision. Um, yeah, so related to sports betting, just sports in general, I mean, things like home runs, RBIs, um, points per game, I mean, just almost an infinite number of different statistics that they can report or that somebody might be interested in with a certain player or a certain team. Um, say in Olympic years, like how many medals does each country get, or what are the performance performance times for races or whatever it may be. Um, yeah, it's kind of like a running joke that like in sports, everybody is a world record holder if you stratify enough, right? It's like this person has the highest batting average of, and anybody named Fred who was born on a Tuesday and in the Northwest or something like that. You hear these kind of crazy stats all the time, and like especially baseball, it seems like is the worst for that. But I think you kind of hear them across the gamut in a lot of different sports. Um, Weather and climate. So shorter or longer term weather patterns. We use these all the time, right? You look up I want to go to Kennywood tomorrow. Well, there's a 60% chance of rain. I'm probably going to go on Sunday, right? If there's a 20% chance of rain, maybe I risk it. If there's a 0% chance of rain, like I'm definitely going. Um, so, looking at things like that, or even a predicted temperature would be another example. It doesn't maybe feel like a statistic, but that is, they're kind of saying on average, I think that, looking at the last week's weather patterns, on average, I think that in a similar scenario, the next day's, say, high temperature would be this number. Um, Hot topic today, economics, things like housing prices, inflation, and housing prices. Just to give an example of how different people can look at essentially the same data set, you know, and for a lot of these are different data sets, but a lot of people, for instance, a lot of people can look at the same data set, the same list of, say, possible descriptive statistics, and then very much disagree on what inferences to make from there, or even what descriptive statistics are the more important or more relevant ones. So consider housing prices, right? Should we look at kind of average housing price in a given market? Should we look at, if I want to live near Pittsburgh, should I only look at houses that are in proper city of Pittsburgh, or should I look at the suburbs? I mean, if we're saying this area is not very affordable, well, people could move 3 miles away, 5 miles away and commute maybe. Should I look at just sale price? Like, what do you have to pay to get this house? Or should I look at price per square foot? Right. So if we want to say that houses are more expensive now than they were, even in real dollars, even taking into account inflation, than they were, say, in 1980, we might ask the question, is that just because houses are bigger today than they were back then? Or is it because houses are actually more expensive per square foot? And do we care about that, right? If you say, oh, well, it's just because houses are bigger today, but all of the houses today are bigger. So if you're going to buy a house, you kind of have your hand forced and have to buy a bigger house. Maybe that's the more relevant side. So that's kind of on the like wisdom side of things, is what is the more important descriptive statistic? We can look at the exact same data, the exact same descriptive statistics. We can agree on all that. And I can say, yeah, I completely agree with you on that. But I think this descriptive statistic, let's say price per square foot, is the more important one to look at. And you might say, I think just overall sale price is the more important one to look at, because whatever, we have different goals in mind, different things we're trying to analyze. We think that the trade-offs, we evaluate the trade-offs differently. Um, or things like, CEO pay, or things like unemployment, particularly, a lot of people are looking at AI and asking, we've seen a bit of disruption, at least it seems, in the last couple of years from AI in terms of employment. Do we think that trend of disruption? Well, number one, do we think the disruption even exists from AI? Number two, if it does exist, do we think the trend is going to, continue? Is it going to just flatten out? Is it like, okay, it had a disruption and now it's just going to stay steady from here on? Do we think that it's going to continue being more disruptive? So trying to look out into the future and say what will happen, right? Some people would argue that a lot of the CEOs who are saying, hey, we cut 10 or 20% of our workforce because of synergies with AI and so on. Well, really, just their business has contracted. And it sounds a lot better to say we implemented AI and have this big win than it does to say, well, our sales went down 20%, so we cut 20% of our workforce. I think there's a little bit of that going on too. Um, but that's another place we could look. Any other thoughts while we're going along here? And speaking of AI and machine learning are hugely, hugely statistics based. Um, you take an enormous amount of data, feed it into a certain type of model, and then out pops, Chat GPT or generative AI or something like that. Um, and it's really important to understand the GIGO idea, garbage in, garbage out. So what we feed into the model is going to influence how the model behaves, right? So if we feed in a whole lot of, let's say, literature from the 17 and 1800s, it's probably going to talk like that, and it's probably going to have those kind of views as its way of thinking, versus if we feed in a lot of data from, say, Facebook discussions, right? So yeah, definitely. Oh, that was already up there on the chat. Sorry. Any other thoughts from your area of interest or anything like that? Yeah, so I think that was most of what I kind of had over here. And then maybe another one, politics. So things like exit polls, predictions, and so on. If you want a good laugh, look up the Count Bin face. He's kind of a joke candidate in the UK that runs for elections. And so he was running against this guy, Nigel Farage, who there's a whole scandal with Farage, and uh, but he actually got like half as many votes as Farage. So like, would it have been predicted that this guy who literally wears a trash can on his head and says that he's an alien from outer space would get half as many votes as the previous the I guess incumbent. He like resigned and then re-ran. It's kind of complicated political maneuver, um, but would anybody have guessed that this goofball would get half as many votes as a real candidate? Would that have been predicted or not? So, all right, I think that about wraps us up for the different applications. Oh, I have this kind of written here twice, but that was what I wanted to do there. Let's talk briefly about some tools or techniques used in the field, and then jump into our Chapter 1 PowerPoint. I think I am going to post the Chapter 1 PowerPoint now. So as I mentioned at the beginning of the class, the Chapter 1 PowerPoint, or the PowerPoints I would normally have on Blackboard, but Blackboard went down last night as I was going to post it. So I posted it in the chat. So this will give you a few minutes if anybody, wants to download it and print it out or something like that. It'll give you a few minutes to make that happen. But we'll talk about some tools and techniques used in statistics, and then we'll jump into Chapter 1. And some of this, as an aside, kind of some of what we've been talking about already is related to Chapter 1. So we've kind of already started a bit of Chapter 1 in this discussion. But we'll see, we'll see that as we go through the PowerPoint slides. Okay, so some tools or techniques. Um, I've actually mentioned several already. And if we think about this picture here, going from, say, raw data, just a list of a bunch of, let's just say, numbers, to something that's a descriptive statistic, to something that's explaining something about that list of numbers, to something that's making an inference, that's making a model. What are some tools that we might use? What are some, in fact, there's one written right on this page. Oh yeah, as somebody mentioned, yeah, he's basically the British equivalent of Vermin Supreme. Vermin Supreme is the guy who wears a boot on his head and has a pony-based economy where everybody will get a pony if he's elected president or whatever he's running for. And um, he has, I forget what a couple of his other things are, but yeah, these joke candidate. The unfortunate thing about the joke candidates is, you know, usually quite often their arguments are about as solid as the as the real candidates' arguments, and that's kind of the reason that they're running as joke candidates. But anyway, um, okay, so what is an example of a tool or technique? There's one right on the screen if you um, need a prompt. So I have my, 2,500 data points for the close for the S&P 500 for the last 10 years. That list of numbers isn't super helpful. Can I boil that down to one number? Can I do something to those 2,500 numbers to give me one number that helps me understand them? So we could compute an average, right? We could talk about the average rate of return or the average price or something like that, or the average height of people in Pittsburgh or whatever it may be. Um, so an average or something like an average, a measure of center, trying to answer a question that's something like, what does the typical data point look like? Also, if you think of stocks, again, if I look at this list of 2,500 numbers, it's really hard for my brain to interpret that. Has the market been going up or going down? Has it been kind of flat? Was there like a big dip in a recovery? Um, but maybe I can draw a graph. Maybe that could be, a graph that looks something like this, or maybe it's something like a histogram, one of these bar charts, right? Like how many days was it? What was the S&P value between these two numbers? Something like that. Any other thoughts on what are some other tools or techniques we could use? We could talk about, say, max or min. What's the highest price the S&P was in the last 10 years, right? Maybe I look at that and I think, okay, I don't think it's going to go above that this next year. I mean, I'm not saying I don't think it will, but I'm saying maybe that's something that somebody could say. Or what's the minimum value, or what's the max or minimum height of the sample that I took of people, and maybe that'll help inform how I should build this kind of seat or engineer this bus or something like that. Uh, we have trend lines or linear models where I might say, look at this, say stock data, and try to fit a linear model to it. This would be called a regression, something that we'll talk about near the end of the course a little bit. What else? Uh, Probabilities or chances, right? A 30% chance of rain tomorrow, or a 50% chance that this team covers the spread, whatever that may be. Um, yeah, and then we have a couple other ideas that are very important, but that most people have not heard of unless you've, say, read medical research or finance research or something. Um, Confidence intervals and hypothesis tests. So this is kind of in a sense what the entire course is really building up to. These are inferential techniques. So they're on kind of like this level over here, making an educated guess about something intrinsic about the real world based on limited data that we have, limited data and whatever descriptive statistics we have. Um, Again, these are techniques that most people have not heard of, um, but that's really what the course is building up to. So really, kind of the first three chapters, kind of roughly speaking, are going to look at descriptive statistics. How do we just say something about the data itself? And there's value in that too. That's a perfectly valuable thing to do in and of its own right. The next basically third of the course, chapters 4 through 6, we'll look at probability. We'll look at establishing a mathematical foundation, and then we'll kind of combine those two ideas to start making inferences, to start making educated guesses about the real world that are hopefully better than just, pure guesses based on, based on the data or whatever. Hopefully it'll give us a procedure um, that has good grounds to make certain guesses in certain ways. And that's really what these are. We're going to bring together that mathematical foundation in chapters 4 through 6 with the idea of data analysis and descriptive statistics in chapters, I guess, more like two and three, but a little bit of chapter 1 as well. Bring those two together, and chapters 7 and 8 talk about confidence intervals and hypothesis tests and making inferences. Okay, so any last thoughts? Anybody want to chime in with a an application or a tool or technique or a thought that is burning a hole in their pocket, or we
Can
can
you
jump
repeat
on.
that last one once again?
Yeah, sure. So we have confidence intervals and hypothesis tests. So just like a hypothesis, like in the scientific method, you establish a hypothesis and do some other things. Same idea here. So hypothesis tests, and then the one above is confidence intervals. So confidence, just like if you walk into a room and you're confident, that kind of same idea, and then interval, like an interval of the real line. So, any other questions, thoughts, anything else? Okay, give me a second here to get my screen share reset. Get the PowerPoint pulled up and all that. Okay, so you all should see the PowerPoint on the left and then our little OneNote over here on the right. When I'm in full screen like this, I hide the chat. So if you want to chime in with something, if you can unmute yourself and say something. Otherwise, I might not see you in the chat. Um, but okay, so let's take a look at our chapter one PowerPoint. Chapter one, Introduction to Statistics. So I think the motivating quote, I know this is two quotes in a day, so we have two quotes for today. The motivating quote, I think for the whole course, and I would argue for all of statistics and even, you know, basically much of the sciences, is this quote from George Box, a statistician, who said essentially all models are wrong, but some are useful. Right. So our goal with statistics is not to come up with perfect models. Our goal is not to, somehow like become God and figure out how the underlying structure works definitively. Our goal is to look at the superficial bits that we can observe, collect the data, and try to establish a model that lets us make good predictions and good guesses. Now, I mean, ideally, that would be close to the actual fundamental model of how the universe or society or whatever works, but that might not necessarily be true. We want to make good guesses that we hopefully won't regret very often. And as I kind of mentioned, this is kind of my definition of statistics, converting nearly useless raw data into a more usable form. I really should say into a more usable form here because we talked about information versus knowledge and so on. Okay, let me shuffle a couple of papers over here and get my notes out. There we go. Okay, so in statistics, we have the idea of a variable. It's a similar idea to just in algebra or something having a variable. It's something that can take on different values. So, a variable could be heights of people in Pittsburgh or say the height of a person in Pittsburgh. You look at this specific example of that, and maybe this person is 5'7" tall. You look at a different specific person in Pittsburgh, and maybe they're 6'1". Right, that variable height of a person in Pittsburgh could take on different values depending on which person in Pittsburgh you were looking at. Data are the values the variables can assume. Random variables are variables whose values are determined by chance. I think I'll talk about that in just a second here. And then a collection of data values. So I have the person that's 5'7", a person that's 6'1", and I've measured 100 different people in Pittsburgh, and I write down all of those heights and I have that on a piece of paper. that collection of data values forms what we call a data set. And when we're dealing with statistics, kind of in this course, our starting point is really, at least mentally, our starting point is we have a data set and then we move forward from there. In chapter one, we'll talk a little bit about how do you get a good data set, how do you make, get one that's representative, things like that. We'll talk a little bit about that in chapter one, but that's more kind of experimental design and so on. We're not going to hit that very hard in this course. We'll talk about it a little bit because it's of interest, but basically, starting in chapter two, we kind of have the mentality that we have a data set that's handed to us. We have that list of the S&P numbers or that list of 100 people's heights in Pittsburgh, and then we want to move forward from there. So that's really the focus of this course. That's the more mathematical side of things. And uh, there is plenty of discussion to be had and coursework to be done in other courses on how do you get that data set in the first place. Randomness. I want to take a moment to talk about this. We'll talk about this a little more in chapter 4. But random variables are variables whose values are determined by chance. So if we think of, something like rolling a die, right? A standard six-sided die, or like a single of a dice, has 6 sides, 1 through 6, equally likely to come up. You throw the die, and it makes sense to model it as equally likely that you come up 1, 2, 3, 4, 5, or 6. When we let go of the die, we don't have any idea of what number is going to come up. Now, some people will look at this and say, well, wait, I mean, let's just forget about quantum mechanics and all that, but we have Newtonian mechanics, right? I mean, can't we, in theory, as soon as I let go of that die, if somebody was, had some fancy computer system and a bunch of cameras and was measuring a bunch of things about the room, whatever the air temperature and air flows and all that. And as soon as I let go of the die, can't this fancy computer system, at least in theory, look at how I let go of the die, where it's going to bounce off of and all that, and say deterministically, with no chance involved, how that die is going to land and what number is going to come up. And at least according to Newtonian mechanics, if we could probably do that, right? We would need better computer systems than we have now and better camera systems and so on, likely. But, at least in the theory, we could do that. So really, when we say variables whose values are determined by chance, or when we talk about randomness, we're talking about a structure that we're imposing. We're saying, okay, I mean, in theory, you might be able to do that. In theory, you might be able to say with no uncertainty how this would end up if you had perfect information and could analyze it perfectly and knew all of the fundamental rules and so on. But in practice, that there are many systems for which that's just, at the very least, infeasible. Uh, and possibly essentially impossible, right? I mean, take measuring all the heights of all the people in Pittsburgh. I could go around to every single person in Pittsburgh and measure their height, but like some people just aren't going to let me, right? They're going to say, no, you can't measure my height. And like, well, now I can't get the heights of every person in Pittsburgh. So randomness, or this idea of chance, is a model that we impose. We say, all right, these systems are too complex to deal with in their full deterministic state. So we say, okay, I throw a die and it comes up 1 through 6 equally likely. Even if in theory, maybe some fancy system could predict exactly how it comes up, in practice, we're not able to do that. Or at the, you know, or even if we are able to do that, maybe we don't want to expend the resources to do that, right? Maybe we could build this system, but I don't really want to, spend $100 million building a system that tells me what number is going to come up on a die or something, right? That's just not a good use of my time and effort when I might be able to get, just as valid a result, using statistics, using this structure of randomness. Okay, so we have two main areas of statistics, as we kind of mentioned before: descriptive and inferential statistics. So descriptive stats, I like to think about this as making things smaller. So we have a data set we start with. It's say a whole bunch of numbers, maybe a bunch of heights, maybe a bunch of S&P numbers, and I want to make that smaller because I can't look at a list of 2,500 numbers and understand anything meaningful about it. But I could look at one number like an average return or one number like a maximum height from this sample, and I can understand that. That's something that I can internalize. So that's kind of what descriptive statistics is in my mind. It's taking something big and making it smaller so it's easier to interpret. Or it's the collection, organization, summarization, presentation of data. Also doing something like maybe making a graph, right? Sometimes a visual representation of that data is easier for me to interpret. Inferential statistics, I think of, again, roughly speaking, as taking something and making it bigger. So I have this 2,500 S&P numbers. I want to know what's going to happen in the next 250 trading days. I want to know something about 2,750 numbers based on this 2,500. Or I have a sample of 1,000 people in Pittsburgh. I have 1,000 people's heights who I measured, and I want to use that 1,000 data points to say something about the 500,000 Pittsburghers. I want to kind of make the statement bigger in a manner of speaking. So that's inferential statistics. Here we often use probability or the chance of an event occurring. And I mentioned confidence intervals and hypothesis testing, which are in some ways closely related to one another. It's a decision-making process for making claims about a population. Okay, so something that I've kind of used this term already, but I've skirted around defining it. Population versus sample. Population consists of all the subjects that are being studied, or really all the subjects that we want to make a claim about. So over here, I might have a population of all Pittsburghers. And again, like uh, in an ideal setting or in a research setting, we would want to define what is a Pittsburgher more carefully. All people that are in Pittsburgh at the moment, or everybody that is in Pittsburgh once a week or more, or people that live in Pittsburgh. But we'll just say kind of all Pittsburghers, right? That's our population. We want to say something about all people who are Pittsburghers, however we want to specifically define that. A sample is a group of subjects selected from the population. So my sample might be the 100 people measured, the 100 people whose heights I went around and measured. That's my sample. That's not all of the Pittsburghers. I didn't measure every individual Pittsburgher by any reasonable definition of what a Pittsburgher is. But those 100 people are, a selection of 100 of the individuals in the population. So we can talk about maybe an average, right? I could talk about the average. I can't spell, apparently. The average height of all Pittsburghers. I could be interested in that. Or I could talk about the average of the data set that I collected. I could talk about the average of these 100, the average height of these 100 people. In both cases, I might refer to it as an average, or if I was being more careful, we'll see later on, maybe I would call it a mean or something like that. But in both cases, I might refer to it as, say, average. But I kind of the scope is different, right? The scope down here, it only applies to the sample. I take these 100 numbers on a page, and to get an average, I think most of us know how to get an average. If you don't, that's fine. We'll cover it in chapter 3. But I would take those 100 numbers, I would add them up, I would divide by 100, and there's my sample average.
Quick
So
question.
that's a sample average, and we call that a statistic. Now, quite often it's the case that I would like to say something about a population, but I don't have access to the whole population's data. What I have access to is a sample. So I might be interested in, you know, knowing something about the average height of all Pittsburghers. This would be a population average. This would be a parameter. So it's a little bit annoying that our subject is called statistics, and the things that are statistics really are the things that correspond to samples. The things that correspond to populations, we call those parameters. It is important to get the terminology correct, though. This is really where things like confidence intervals and hypothesis testing, um, it's where they really shine, I guess, in a sense. It's in connecting these two ideas. So why do we care about populations versus samples? Well, usually what we want is the population parameter. Like if I was omniscient, if I could just, know what I wanted to know, I would just know the average height of all Pittsburghers, or maybe I would have a data set that is just all Pittsburghers, and I'd have the information or the data and the information for the whole population. But in practice, that's very rarely possible or feasible. Even if it's possible, it might be, cost 100 times as much to get that data. But maybe I could do a perfectly good job with just a sample that's 1% is large and 1% is costly. So in practice, I typically want population information, but actually have sample information. And kind of, really a large part of the course is how do we connect the two? I want to use this sample data and information to say something about the population information that I actually want. So how do I do that? And that's really kind of what the course basically builds up to. But this is a really important distinction that we have a population, that's the group of folks or group of subjects, it doesn't have to be people, that we want to say something about. We want to make a statement. The average height of all Pittsburghers is, 5 feet, 8 inches tall or something. And what we have access to almost all the time is just a sample. It's some of the individual subjects in that population, but not all of them. So what we actually have are statistics, and what we want are parameters. And the question is, how can I leverage the statistics that I have and some mathematical background to make a guess about what I think the parameter actually is? And so I give another example here. So suppose we took a sample of 1,347 people from a population of, let's just say, all Americans. And we say of the 1,347 people sampled, in other words, of just this data set, 12% of them were found to be diabetic. That's an example of descriptive statistics, right? It's taking that 1347 and just kind of crunching it down and giving you one number. But the statement that sounds very similar, based on a study involving 1347 people, we estimate that 12% of Americans are diabetic. Now we're taking that 1,300 person sample and trying to blow it up to 350 million people to say something about all of them. That's an example of inferential statistics. And just to clarify, in this case, we might be saying that the population the population parameter is the percent of Americans who are diabetic, and the population would be all Americans. And then the sample was these 1,347 people who were plucked from the population. Okay, any questions so far?
All right. So is the inferential stats just going from a from a statistic to a parameter?
Yeah, basically. So basically inferential stats takes us from a statistic to a parameter. Yeah. Yeah, sure. Okay, let's move on then to variables and types of data. Okay, so a little bit of a note about this section. It might seem at first that we're introducing all this terminology, and why are we introducing all of this, especially in a math course? Why do we hear about this? And there actually is a good reason for this. It's because by thinking about this terminology, it lets us think about variables and data um, a little more rigorously. And then later on, when we get to say chapter 2 or chapter 3, and we have to decide, okay, I have a bunch of different graphical techniques I could use. I could make a pie chart. I could make like a histogram or column chart. I could make one of those like line graphs like you see with stock prices. This is what my data is. Which one of those graphing techniques is most appropriate for this data? Right? Or maybe I look in chapter 3 and I say, okay, I could report an average, I could report a median or a mode, or I could report a bunch of different, say, similar things that are kind of like an average. Which one of those would be most appropriate for this data? And the answer to that relies a lot on the discussion we're going to have now. What type of variable is it that we're trying to model or describe? Okay, so the first distinction we have is qualitative versus quantitative variables. So quantitative variables, if you think of like quantity, that means like amount. That's kind of numerical in a manner of speaking. And qualitative, so quality is like something that's maybe a little more abstract, right? So qualitative sometimes are called categorical variables, and these are variables where the values can be placed into distinct categories, where quantitative variables are numerical, or at least like numbers, and have a natural ordering or ranking. Uh, so for example, something like, say, color of your shirt. So say somebody is a buyer for Macy's. Is Macy's even around? Did they get bought out? I don't know. So many companies are getting bought out these days. And they say, okay, this clothing line has, they have this shirt in 4 different colors. You know, what do I think the demand is going to be for each of these colors? Well, if the colors are, red, blue, green, yellow, or something, uh, those are the colors. uh, these don't have a natural ranking of any sort, right? It's not like that the red shirt is like greater than the blue shirt or something like that. Um, but they're just in different categories. On the other hand, if I think of quantitative, maybe I'm thinking of something like speed, right? I'm driving down the road in the car, and you know, one car is going 30 miles an hour and another car is going 40 miles an hour. Well, the one traveling at 40 is going faster than the 30. There's a ranking. If I'm interested in how fast are they going, the one going 40 is faster than the one going 30. Um, so these are numerical or at least number like and have a natural ordering or ranking. Does anybody else want to chime in with some with an example of a variable, something we might be interested in measuring, and whether you think it would be quantitative, numerical, and rankable, or more qualitative. Any thoughts? Right.
You were gonna look at like the number of people who went to a ball game, that would be uh quantitative.
Yeah, yeah, definitely. Yeah, so a great example, attendance at a game, the number of people who went to a certain ball game would be quantitative. You know, if this game had 30,000 attendees and that game had 20,000 attendees, the 30,000 had more attendees than the 20,000.
Would qualitative then be like this person spent this much money so that they were then like ranked higher at that ball game, or no? Like at a concession stand or something.
Yeah, I think amount of money spent would probably still be quantitative because if we
Okay.
think like if one measurement was say 30 and another was 40 or something, the 40 would still have spent more money than the 30. So, but that's a good example though is amount spent.
So if you were trying to find like percentage of people that spent money, that would not be qualitative, that'd be quantitative.
If it's the amount of money spent, I would put it in quantitative. If
Okay.
you were just saying like, did they spend money or not? Um, I almost think you could go either way on that one, depending on how you wanted to view it. So we're going to see that there are maybe some gray areas here. But if it
Okay.
was like amount of money spent, you probably have a lot of zeros, and then uh, then kind of something that would behave a little more quantitatively from that point forward. But we're going to stick with, I think, quantitative for that one just because that fits a little better into our model over here.
So would
Professor, I was
most
gonna
like
say,
yes or no?
sorry
Oh,
about that. Go ahead.
No, you can go.
I was gonna say, so the quantitative would be like how many people joined the game, and the qualitative would be like how many people from the city versus out in the suburbs that attended the game.
yeah, yeah. So yeah, qualitative might be like uh, what would you call that? Like residency, I guess. Where you.
Yes, like more people from the city would go to the games downtown versus the people on the outskirts of the surrounding suburbs.
Yeah, yeah. So if we looked at an attendee and we said, are they do they live in the city or outside of the city or um, what location in the greater area do they live? Do they come from? Yeah, that would be qualitative. Yeah, if we said like in the city versus out of the city, these are two distinct categories, but there's no real ranking or anything to them. Or if we said, what neighborhood are you from? There's no real ranking to those. I mean, we could impose a ranking. We could like put them in alphabetical order just so that we have a way to list them. But that ranking doesn't really have anything to do with really anything that we would be interested in um, knowing about if we were, say, asking, what area should we market to or something like that. Um, this area starting with A instead of Z isn't going to impact that with much likelihood.
So would most yes no questions or yes no surveys be qualitative?
Um, yeah, probably. Um, one of the issues is that when you're saying yes, no, you're talking about more of the answers to a question and less about what the variable actually is, right? Um, so kind of, I'll give maybe an example. Um, so if you think about something like zip code's a number, right? But would that be quantitative or qualitative?
quantitative.
Yeah, it feels like it's quantitative because it's a number, but is it like,
I guess it would be qualitative because it's
yeah,
like
it's
random.
probably qualitative. So it looks like a number, but it's at least in the vast majority, I would say, of uses, it's going to be qualitative. Now, you might argue that, like, okay, the ones are on the east and the nines are on the west, so there's a little bit of a natural ordering there, but at least, within a city or a state, I think they basically just go by alphabetical order, more or less. Um, so yeah, and not the whole zip code, like part of the zip code does have to do with like actually where you are geographically, and another part of the zip code is just kind of enumerating the different neighborhoods. Um, so if I look at the zip code, like say 15211, where I grew up, it's like, okay, well, you know, is 15211 qualitative or quantitative? That it kind of depends on what the context is, right? If I said, um, how many people attended this like high school game, if it was, or maybe college game, 15,211 people, then that's going to be quantitative. If 15211 represents a zip code, that's going to be qualitative, most likely. Let's think about some other examples, and feel free to chime in if you have any other thoughts. But so something like number of students in class. Um, Something like we talked about, well, heights of people in Pittsburgh. So height would be a quantitative variable. If one person is 6 feet tall and another person is 5 feet tall, the 6 foot tall person is taller than the 5 foot tall person. So it's numerical. It has kind of a natural ranking. Um, so die roll.
So can like nationality fall into qualitative?
Yeah, definitely. So nationality. Say something like, what country are you a citizen of? What country were you born in? Something like that. Yep, definitely. Die roll result, we probably in most cases where we roll a die for something, we would think of that as quantitative. Like if we're thinking of number of spaces you would move on a game or something like that, that's probably quantitative. Um, I have my wrong set of notes out here, so that's why I'm a little discombobulated. But um, yeah, something like religion or religious affiliation would probably be qualitative. Um, so something like think about maybe grade as in like a course grade as a percent. We would definitely say that's quantitative, right? If I say your final course grade was a 93% or something. What about like a letter grade? It's not a number if I say your final course grade is A, but it really behaves more like a quantitative variable, right? So let's think a little bit about this. In what, and we're going to talk more about these descriptive techniques in chapter 2, but where might we want to use this delineation? We might say something like, if I have a histogram, if I want to know maybe number of students with each grade, and I write a histogram out, I probably wouldn't want to do, here's my number of students. I probably wouldn't want to do like B, F, A, C, D. Like that would be a confusing graph to look at, right? if I made my histogram like that. That's probably not so great. I probably would want to do something like A, B, C, D, F, or perhaps the other way, maybe F, D, C, B, A. But because there's kind of this natural ordering, yeah, I probably want to respect that ordering a little bit, right? On the other hand, if I had, say, just the color of shirts in a department store, if I had whatever I said, red, blue, green, and yellow, does red, blue, green, yellow, does that make sense? Yeah, sure. Could I have done blue, green, yellow, red? That would make just as much sense. Right. So when I'm say, for instance, constructing a histogram, a bar chart or a column chart, if I have a qualitative variable, it probably doesn't matter what order I put the bars in. If I have a quantitative variable and if I also think that a bar chart is the uh, you know, proper graph to use, well, if it's quantitative, it has a natural ranking, a natural order. I probably want to respect that order. So this would probably not be a great graph. It would probably be misleading or difficult for somebody to interpret. This one would be much better, or perhaps FDCVA, but I probably want to respect that order at least in one way or another. Right. Same thing with, say, a die roll result, rolling 1, 2, 3, 4, 5, 6. If you're thinking about like how many spaces do I get to move, or like if a better roll gives you some kind of advantage or something, I probably want to respect that. If I'm just rolling a die because, you know, um, whatever I have six cans of pop that are different flavors, and I want to pick one and I have trouble making decisions, so I roll a die. Well, maybe that die roll result really relates to a qualitative variable. But things like, soda flavor or something like that is qualitative, right? Pepsi or Coke or root beer or something like that. These would be qualitative. Although there's almost like so many soda flavors anymore that it's almost a continuum. I don't know. I feel like I'm waiting for them to come out with 50% Coke and 50% Pepsi or something, or I don't know. Um, I think that's probably enough examples for these two. Oh, there's one other one I want to throw in here. If we think about something like, say, annual salary, right, that would be quantitative. And maybe, say job type, are you an accountant? Are you a teacher? That kind of thing would be qualitative. So we'll kind of throw that in here because that'll be a bit of a discussion later on. I'm going to erase these graphs down here. But I wanted to show you those graphs just to give you a little bit of a uh, preview of why this might matter. Okay, so the next way that we can think about variables is discrete versus continuous. So qualitative variables are basically their own category over here. And then quantitative variables we can split into discrete versus continuous. So discrete variables assume only values that can be counted. And continuous variables can assume an infinite number of values between any two specific values. They're obtained by measuring, often include fractions and decimals, and they have to be rounded. So this can be a little bit hard to internalize. The first thing that I want to do is to say something that this is not, what we're not talking about, because this is, people see the word continuous and they immediately often jump to this idea. We're not asking the question, are we done collecting the data, right? So some people will look at, um, I don't know, let's say like number of students in a class, and they'll say like in a class meeting, they'll say, well, once the class meeting's over, you know the number of students that were in the class, but if you are measuring stock prices, it keeps going. That's not what we're talking about with discrete or continuous. That's not the sense in which we mean continuous. The sense in which we mean continuous is more in the sense of like density of possible variable values. So discrete value variables, another way of thinking about it is there's like a first possible number that can be put in for that variable. And then there's a second possible answer and the third possible answer. Where a continuous variable, there's no such idea. If I have, you know, this number and this number that could be values for that variable, there's a number in the middle that could also be a valid value. So does anybody want to take a stab at, of these quantitative variables we have listed here, what's one that you would say is clearly a discrete variable where there's like a first possible number for the value of that variable, a second possible number, a third possible number, and so on? Pick one that's kind of an easy one. Any thoughts? I think the easiest one here is probably number of students in a class. This is discrete. How many students can I have, let's say, like in a class meeting? I could have zero. There could be zero students attending. Maybe next class there will be zero students attending. I don't know. I could have one student attending. I could have two or three or four. If I think of zero and one students, is it in any way reasonably possible to have a meaningful answer in the middle? Can I have a half a student in attendance? Well, no, that doesn't make any sense, right? Can I have, 9 3/4 students in attendance? No, that doesn't make sense. I can have nine, I can have 10, but I can't have anything between 9 and 10. That's a discrete variable. Now, height, on the other hand, this would be continuous. Somebody can be 60 inches tall, 60. Somebody can be 61 inches tall. Those are two valid heights. That's fine, 5 feet tall and 5'1". But somebody could be 60.5 inches tall. That's another perfectly valid height. Somebody could be 60.1 inches tall or 60.01 inches tall. Pick any two numbers that of height a person could be. And for instance, take halfway between those, and that's another valid height, or take 3/4 of the way between them, and that's another valid height. Right? Another way to think about it is if I say, okay, this person's 60 inches tall, what's the next allowable value for height? That doesn't make any sense, right? If I say there are 10 students in this class, what's the next possible number of students? It's 11. You can't have 10 1/4 students. But you could have 60 1/4 inches or 60.1 inches or 60.05 inches. If we look at 60 inches, there's no next admissible value of height. Now we might choose to round to the nearest inch, but that's a choice that we're making, right? That's not inherent to the data that we're collecting. That's a choice in how we either measure or record the data. So our measuring device, our tape measure, might only, go down to a half an inch or a quarter of an inch or something, or we might have to, at some point, be more precise about what do we even mean by height, right? Like, do they have to take their shoes off? Does their hair count? But the idea is that if we're measuring height, that's a continuous variable because two different ideas. Between any two valid heights, there are more heights that are also valid. And also, if you take a specific height, there's no next admissible value of height. Where a number of students in a class is discrete because between many sets of two numbers, say 10 and 11 students, there's no other admissible value of students in class. You can't have 10 1/2 or 10 3/4 students. Or another way of looking at it is if you take a certain number of students in class, like 10, there's a next allowable. That makes sense. 11 is the next allowable. And from 11, 12 is the next allowable value for that variable. So with that clarification, does anybody want to take a stab at a different one?
Would die roll be discrete? Do I roll
Yeah,
and grade?
definitely.
Grade as in
Yeah.
letter?
Yeah, we can roll a one. What's the next allowable roll? A two. What's the next allowable? A three. If we consider two and three, is there anything between there we can roll? Well, no, we can't roll a two and a half. Exactly. Yeah. Any other thoughts?
Like precise percentages that could go up to like 92.2% or
Yeah, yeah. So grade as a percent would be continuous. Yeah, you could get 92% or 93%, but you could also get 92.5% or 92.1% or right. What about letter grade?
discrete.
Yeah, discrete. You get A, B, C, D, F. Even if you do pluses or minuses, like we don't do pluses or minuses at CCAC, but some colleges do, right? If you're at a C plus, the next, like if you want to go up one increment, you could go to a B minus from a C plus, but you can't get like a C plus plus or a B minus minus or something, right? Um, so even if you have the plus minus system, there's more gradations, there's more possible values for the variable, but they do have that kind of strict delineation. There's a next for each value that you're considering, or you can find two values like say C and C plus where there's nothing in between. Or for our system, A, B, C, D, F, C, the next one up you can go is B. Um, yeah, so if you're thinking of the grade as a letter, then that's going to be discrete. As a percent, that's going to be continuous. What do you think about speed? Like how many miles per hour you're going in a car, something like that. Well, it's going to be continuous, right? You can go 40 miles an hour, you can go 40.1 miles an hour, or 40.01 miles an hour. In fact, like most physical quantities that we measure, most of them are continuous. Things like speed or height or weight or distance or length or, these kind of things. They do tend to be continuous. So continuous, and that's not a hard and fast rule, but that's just kind of most of the time physical quantities tend to be continuous. And most of the time, things that start with number of, whether explicitly or implicitly, are discrete. So, for instance, number of students in class or number of cars in a parking lot or whatever it may be. Amount of money spent at a vendor at a game would be continuous. Now, here's an interesting question. At least, I think most of the time would be continuous. If the vendor only sold whatever, hot dogs at $10 per dog and they sold nothing else, and you say, well, I mean, maybe I could treat that as discrete because it's like because what you pay is essentially just the question of the number of hot dogs you bought, right? So you could kind of maybe equate those two and make an argument that it should be discrete. But and I would say the vast majority of practical situations, this would be like a continuous number. You could, kind of spend more or less any amount of money at a stand. Now, attendance at a game, I'm going to come back to that. An annual salary. These two are a kind of a little tricky. So let's think about annual salary. Can somebody make an argument for why it should be discrete?
Because you can't like make half a cent or
Yeah, exactly. I mean, yeah, you can't be paid half a cent. So on one hand, we say what's discrete, right? You could make 50,000 and 0 cents, or 50,000 and 1 cent, or 50,000 and 2 cents per year, and so on. So I can enumerate them all. What's the next one up from $50,000? Well, your boss can't give you a half a cent raise, even if they would prefer to. It's $50,000 and 1 cent. Can anybody make an argument for why it might make more sense to think of this as a continuous variable?
Because for discrete variables, it would be easier to assume it for the what's it called? There'd be less variables going on. The point continuous is that you simplify it and make it more streamlined.
Yeah. So like imagine that we want to make we have this discrete variable like letter grades, right? A, B, C, D, F. I mean that kind of makes sense. I can make a nice histogram out of that. Can I make a nice histogram out of, how many people had a salary of exactly $0? None. How many had 1 cent, 2 cent? I'd have like a whole bunch of zeros and then like a bar here at whatever, 11,142.73. And then a whole bunch more zeros and then like one, like that's just a dumb graph, right? That doesn't make that, that uh there are too many increments, right? This increment is in the seventh significant figure. If you consider like height, which is a continuous variable, we're not going to report seven significant figures of height. We're not going to say that somebody is 60 point, 0.38447 inches tall. Like we're going to report height as maybe three sig figs, right? Like 60.1 inches, maybe even four, but never this many. So we could call this kind of continuous as well, right? There are so many gradations that going from $50,000 and 0 cents to 1 cent like doesn't make any practical difference. Um, so we almost treat it more like a continuous variable where the gradations are so small that it makes a lot more sense to model it or to draw a graph or something as if it was more like one of these numbers than like a number of students in class that's probably going to be stuck between about 0 and 40 essentially all the time. Okay, so that wraps us up for today's lecture. Let me stop the recording.